Okay, so on we go to segmentation. Conceptually, this is the sort of capability segmentation is supposed to achieve. You're supposed to be able to have some memory space, and it's broken up into a bunch of different segments going every which way. But basically, each of these segment registers, of which you have 6, each segment register will select from many different segment descriptors. So there's a bunch of these structures which describe different ways that you can chunk up memory. And so 6 of them could potentially be active at one time. And so for each of those, it would be basically something like the CS, or code segment register, would say, okay, here's the base address of my code segment, and here's the limit. So you take the base plus the limit, and you get some chunk of memory. And we're going to say that's all code. And so built into segmentation is already the security notions of code segments are executable and readable, but not writable. Okay, so these things already, segmentation already implements this sort of notion of non-executable data and non-writable code. So as I just said, if you have something which is a data segment, some segment register will select one of these descriptors, and the descriptor will say, here's where data starts, here's where data ends. And built into this is the notion that all data segments are non-executable. So you could do a jump over to some data segment, but it's not going to execute code there. Yes?
So is it the access field there that indicates whether it's code or data?
This is sort of just it would be some other thing other than the base and limit, but it's the structures are going to look sort of different than that. So it's not strictly just access. There's a few different fields and stuff in there, but yes, the chunk of the descriptor other than the base and the limit is going to describe whether or not it's code, whether it's data, whether it's some other things, and what ring it's in. So basically there's this notion of linear address space. We're going to be using these terms like linear address space and linear addresses and stuff a bit throughout. So the thing you need to know about linear address spaces is that eventually you can think of it like the virtual memory address space. For now, a linear address maps one-to-one to a physical address. So until we talk about paging, a linear address is just a physical address. So the segmentation, therefore, are taking chunks of physical memory and assigning them permissions like your code, your data, and your ring 0, your ring 3, stuff like that. So to locate a byte, so if you're trying to find memory in some segment, you use what's called a logical address. So, and this is going to be a key point in this class, is that in reality, no matter what you've learned about virtual memory addresses before and things like that, all memory access by the hardware uses these logical addresses. And a logical address, also called a far pointer, so it's potentially, well, it doesn't matter. Just far pointer is another name for it. A logical address consists of a segment selector and an offset into the segment which is being selected. So if you're specifying a logical address, you say, I want that segment, and I want this offset into that segment. The segment selector is 16 bits, and the offset is 32 bits. We'll say that again later when we have pictures. So a logical address, though, is a 48-bit address, and all hardware is actually using these 40-bit segment selector plus 32-bit offset. The physical address range, since we were talking about linear addresses, the physical address range is defined based on, whatever you can actually try to go talk out to RAM on the memory bus. That's your physical address space. We talked about that in CPUID. We said it should tell you what your physical address range is, what addresses can actually be talked to in real RAM chips. But for a normal system, we think of it as being just, for a normal protected mode system, you think of it just being 2 to 32. You've got 4 gigabytes of maximum address range in the normal 32-bit system on Intel. And later on, we'll see physical address extensions, which kicks that up to 36 bits, but not all at once. All right. And obviously, don't worry about it. All right, so the linear address space that we're saying right now is just physical address is a flat 32-bit space. But when we only have physical addresses, that 32 bits is reduced to however much physical address space, physical RAM you actually have. And so, as I said before, when paging is disabled, which as far as we care right now it is, linear addresses map one-to-one to physical addresses. Right now, we have some notion of logical addresses mapped to linear addresses. And all memory access is actually logical addresses. And so we said logical addresses are a segment selector and a 32-bit offset into that segment. The segment selector, which is stored in one of those segment registers, it's selecting from some big table of those descriptors. So here, it's explicitly calling out and saying there's a descriptor table, and I select into that, and then I pull out a base address from that, and I add that to my 32-bit offset. So going back to this picture, for instance, there's some table of these segment descriptors right here in the middle, and it's just a big array saying, like, here's one segment, here's another segment, and it just specifies how they look in memory. And these segment registers store segment selectors, which are saying, here's some offset into the table, and that's the segment descriptor I want. And then you basically take, when you're trying to access memory, you're not just giving a segment selector, you're not just saying, I want to access memory in this segment, you're saying, I want to access memory in that segment at some offset into the segment. So this is sort of, this picture is critical to understand, and we'll be coming back to it again later to re-emphasize this. But first you got to pick which segment you want to deal with. Then you got to say how much of an offset it's going to be into that segment. That gives you a linear address. And for right now, we say linear addresses are just physical addresses. So that just gives you the actual address in RAM where your data is. That gives you the address in RAM where your code bytes are. All right. So in the big picture of things, this is then how it looks. And right now, this is the wool pulled over your eyes. This is where paging would be. But since we have no paging, right now, this logical address up here, aka far pointer, where you have a segment selector and an offset. Take segment selector, pick something out of a table. Now we're adding in these table names. There's a table called the global descriptor table, and there's another one. So you say, I want to pick this description of a segment out of this table. And then I want to add this offset into that segment. So if this table, if we selected this segment descriptor right here, and it says, hey, my segment starts at 1230000, and then you say, and I want offset 123. You take base 123000 plus 32-bit offset 123, and you get 123123. And then that's the actual linear address which you're trying to access. And since there is no paging, the hardware goes out to physical RAM and tries to access, a D word or a byte or whatever of the physical RAM at address 123123. All right. So now we have to understand how those segment selectors work, because they start the process off for us, right? They say, I want this 32-bit offset to be in the context of some segment. And so which segment? Where is it? How do I find it? That's handled by the segment selector. So a segment selector is a 16-bit value held in the 16-bit segment register. So in this picture, we said we got a bunch of segment registers, and they're just pointing at some descriptor. And so these are just, each of these registers is just 16 bits. So you got a 16-bit CS, SS, DS, etc. And we'll sort of describe the conventions that go along with each of those in a second. It's not even convention. We'll describe the way the hardware uses those. But so you've got up to 6 of these 16-bit registers, and each of them is potentially has a segment selector, which is a 16-bit data structure that we saw on this page. So now we're talking about the 16-bit data structure, which is held inside of one of these segment registers. Fairly simple data structure. It's only got 3 fields. The first field is 2-bit field. It's called RPL, or requested privilege level. 2-bit field, meaning that it can hold values 0 through 3. We might think that this privilege level thing may have something to do with ring 0, ring 3, etc. But right now, just put that on your mental stack. We've got a 2-bit, 2 bits, the least significant 2 bits in a segment selector are saying something about the requested privilege level. Then we have 1 bit, the table indicator bit. And this turns out to specify there's 2 different tables I can select from when I want to go find a descriptor. One of them is called the GDT, the global descriptor table. And this is something which is used in every process in the kernel, everything else. But in some cases, the OS may want to have segments which are specific to a given process. And in that case, what it uses is something called the LDT, the local descriptor table. And so if you want there to be some chunk of this process's memory, which is marked as, non-executable data, then you use the LDT for that process, and basically the OS will swap in and out different LDTs when it swaps around different processes. Yes?
So are particular segments potentially available in both the global and the local descriptor table?
You could duplicate things between the two of them. So if you mean, you could certainly have index 0 in the global descriptor table look the exact same as index 0 in the local descriptor table, but there would be no point to it. Because you can always access the GDT entries from anything. If you have something that you would put in both, just put it in the GDT and use that one. You only want stuff in the LDT to be whatever is specific to that process, which isn't necessarily accessible by any other process.
So the global descriptor table is accessible to everything in the system, and it's not global in the sense of containing all memory segments in the system.
Correct. Yes. It's only global in the sense that everyone sees the same thing with the GDT, but for the LDT, the OS has the option. It turns out not to use that option, at least on Windows, but it has the option of swapping in and out different LDTs for different processes so that they can see memory segments differently from their neighbor. So the table indicator just says, for this, if my CS register right now is pointing at some segment, first I go to this table indicator and I say, is this an index into the GDT or LDT? And then I take these top 13 bits and I say, that's my index into the GDT or LDT. So pick your table based on the table indicator, and then pick your offset into that table, where the offset is, it's an array of these descriptors. You've got one descriptor, one descriptor, one descriptor. So index 0 is 0 offset. Index 1 is 8 bytes offset, because each of them is 8 bytes.
So since Windows never uses the LDT,
Yes.
do any other OSs that you know
I
of?
think Linux uses the LDT. I'm not 100% certain on that. I've seen reference to the fact that there's some virtualization detection things which look at the LDT information, and that it's different inside of VM than it's not on Linux. But that definitely is not the case on Windows, so I'm assuming this virtualization detection stuff, it is the case on Linux, but I've never really confirmed it. We'll talk about at the very end of this slide deck. There's a reference to the virtualization detection stuff that did say, hey, look, the LDT is different in my VM. They are up to 2 to the 13 entries. So yes, they can hold up to these 8,000 possible descriptors. So you can have 8,000 for everyone, and then each process can have another 8,000 specific to it. Well, slightly less than that, because it turns out the LDT is actually in the GDT. So in order to find the LDT, you have to go into the GDT, stuff like that. So a little less than 16,000. Well, certainly more than 16,000 for every process. Still, that's potentially limited. All right. So if we dig down into each of those segment registers themselves, we said, first of all, again, segment registers are just holding one of those 16-bit descriptor things. And the hardware is always using, whatever CS is pointing at or SS is pointing at. It's saying, oh, look, if I want to find CS stuff, I go to table indicator. That says GDT, and you want index, 5, that sort of thing. So the code segment selector, the important thing here is that the hardware always uses the code segment. Whatever segment selector you've got in CS right now, the hardware is going to walk these tables and cache the information. It's going to walk the table and say, if you're trying to execute code somewhere at some logical address, the hardware is always implicitly using the CS. So if you don't say anything else, the hardware will implicitly use the CS segment selector. So if you just think that you're jumping to address, 123, in reality, the hardware is saying, okay, well, code that's running right now, what's your CS set to? Your CS is selecting this segment. And so if you want to jump to 123, 123, I will add that to the base of whatever's in CS right now. So CS is always implicitly being used by the hardware to say, this is the base of your segment for code access. So I think we're going to see this a little later, too. I don't think we really had a notion of it in the first class, but the processor differentiates between code access and data access. When you're jumping around and your EIP is changing, the address of the next instruction in EIP is changing, that's a code access thing. The hardware knows EIP is about, where do I need to pull from memory to get code instructions. So it treats that one way, dealing with the CS register. For data access, when you're just saying, hey, move data from here to there, it's then implicitly using this SS. It's calling it the stack segment, and yes, the DS is called the data segment. But when you dig down into it, all data access, if you do not specify your own segment that you want to deal in. So we saw before with that, well, just to quickly diverge, we saw with that rep move S and rep store S, or rep stos, rep move S. If you look at the actual instructions, they are actually specifying a specific segment. One of them says, you know, always move to destination at DS colon something. That's a logical address. It's saying, take whatever DS is, treat that as my segment selector, take that, you know, brackets, EDI, treat that as the 32-bit offset into that segment. So in that case, there's actually an instruction which is explicitly, you'll see it in the disassemblers, they'll write that showing you that this always uses a certain segment. And it turns out to actually use in the rep move S, it's like using DS and ES. So it's technically copying between two different segments, but in reality, the OS sets it up so that they're the exact same segment. Doesn't actually make a difference. Yes?
Gino? Can the segments overlap so you can treat code as data and data as code?
Absolutely, yes. So the segments can overlap. In fact, they can completely overlap. And in that way, code can be data and data can be code. Yes. But I don't want to spoil the surprise for later. All right. So yep, segments can overlap. So you can have a base address of one, base address of the same. I mean, the fact that I just said that in reality the OS makes DS and ES the same so that when you're rep moving, it's really just functionally moving from one space. Those DS and ES, they're both the exact same completely overlapped memory segments. But the point is you could envision scenarios where you have completely separate segments, non-overlapping, and you want to copy out of one segment into the other segment. So you need to set ES to whatever and set DS to whatever, and then you're copying between them if you're trying to enforce extra protections, for instance. But back to the point about SS. In reality, although it's called SS, the hardware is using SS, the stack segment, for all data access. So I said, if it's trying, you know, if the hardware is looking for EIP for new instructions, it's actually using CS. All code access implicitly uses CS if you don't tell it otherwise. All data access implicitly uses SS if you don't tell it otherwise. And the only thing, yeah, I know, that doesn't matter. Yes?
Where's the stack actually ending up?
Where, sorry, say again, where is this?
Where is the stack actually ending up? We're not using the cleverly named stack segment to indicate which section of memory is the stack.
Somewhere in the stack segment. So all of your data and all of your, say, if I say that everything implicitly is using SS, it turns out that all of your data and all of your stack and everything else is actually somewhere within that stack segment. And we'll get to that later, how it all works out, but it definitely does work out. So it'll all become clear at the very end when I spoil everything. But for now, you just think that an OS wanting to set up something that this is code and this is data, they can say, you know, my code is based at 0, goes to, you know, 2 gigs or something, and my data is based at 2 gigs and goes to 4 gigs. And you can really have those completely separate, and anytime you access code or anytime you access data, they're completely separate. All right, so then DS, it stands for data segment, and ES, yeah, it stands for extra segment. And then there's FSGS, those don't stand for anything, they're just some extra things. So in reality, you can think of DS through GS as just like general purpose segment registers to use for whatever you want. Because CS and SS are used by the hardware for data operations and code operations. The rest of them, you're free to put whatever you want, select whatever segment you want, and then, you know, maybe you want to jump to DS colon something, right? Maybe you want to jump between segments, call between segments, access data in different segments, etc. It all depends on what the operating system is actually trying to achieve. So, but the only key point I want you to take away from this slide is that, and I mean, this was new to me when I dug into really understanding this stuff, is that the hardware is really using CS. For all of those nice times when you see instructions, if you're not saying override CS and use my segment, it's actually using CS for all code jumps, returns, calls. And if you're saying, you know, just move, you know, some if you're just saying, move from memory to register or something like that, if you don't say move, GS colon address to register EAX, it's just using SS. So wherever SS is, it's going to offset into that stack segment. All right, so one point I would say here is that there's the visible part. So in terms of how the hardware actually uses it, there's what's called the visible part, which is the segment selector, that's 16 bits. But because you don't want, this will be a recurring theme, hardware doesn't want to keep walking tables all the time and always have to go out and find stuff. So in reality, when you specify some code segment selector, you put a segment selector in CS, the hardware will walk it once. It will go to the offset in whatever table you ask it to. But then it actually caches the information in what's called the hidden part. And so it caches that entire descriptor out of that table. So it takes the table information, pulls it all into this hidden part. And you can't access the hidden part, but the hardware is using it. But you can't access the visible part. So that's just one point, that once you've accessed something in the code segment once, the hardware forevermore is really just consulting this right here. And we'll see an example of that sort of, let's not walk the tables, let's just cache it later in an attack. All right, so this again is just what I was saying. So in reality, even if you say, move ESP, in reality, or even, you're pushing or popping, in reality, it's always SS ESP if you don't specify otherwise. EIP is always CS EIP. And this is, so this is what I was wanting to try to say. I mean, we could go look at an actual disassembly example to confirm it as well. But when you look at the actual instruction manual for MoveS, it says move, EX or CX double words from DS, that's specifying a segment, colon, ESI, going to memory at that location. So it's saying that's a logical address. So it's using a logical address, 16-bit segment selector stored in the DS register, 32-bit offset here stored in the ESI, and it's going to memory at that location. So this is a rare example where they will explicitly call out, hey, this is copying from two different segments. So if you don't want them to be different, set them to be the same thing. If you do want them to be different, make sure you change DS and ES. All right. And again, if you want to override things, you can. In inline assembly, it would really just usually look like tacking on a segment register, colon, 32-bit offset. So in that way, if you know there's some, and this will, the reverse engineers will be familiar with this. If you know there's, for instance, some data structure stored at the base of FS, as is the case in Windows, you can just say FS colon bracket 0, and then wherever that data structure is, well, let me just skip to the chase here. In Windows, by convention, Windows always exports a big data structure to every different process. They each get this, I think it's thread environment block. So they have what's called the thread environment block, and every process, when Windows lets that process run, it makes sure to always set up the segmentation information so that the FS segment selector is selecting a segment where the base points at this data structure. So when you access FS brackets 0, you're accessing the first element of the data structure. You're accessing FS brackets 32, you're accessing, 32 bytes in or whatever else. So when you're reverse engineering on Windows, you'll see this frequently. You'll see code accessing the thread environment block tab, and maybe it'll walk some number of things in, get a pointer, pull out the PEB process environment block, and then it'll start accessing that, etc. We actually in the, we didn't dwell on this, but in the Life of Binaries class, virus code and I think something else. Well, in the Life of Binaries class, in the virus code, in order to find some data structures in memory, I use the thread environment block by just doing something like FS0, and I walk to the data structures. So if you go back and we look at the virus code, you'll now be able to see this little thing. And I at that time thanked Corey because he pointed out this was in actually an exploit tutorial talking about different types of shellcode, because accessing this data structure, knowing that this data structure, no matter what process you're in, is always based at FS, because Windows just does that by convention. That's useful for viruses and exploits to know okay, from there, whatever data is in that data structure, some of it's useful to me, some of it's not. But if there's something useful to me, such as a linked list saying, here's where my module is loaded in memory, here's where kernel32.dll is loaded in memory, here's where ntdll.dll is loaded in memory. So you can find like the list of loaded modules in a user space process by accessing this FS data structure.
Zeno?
Yes.
We do have a question on the chat from Dave.
All right. So he's asking whether the opcode would be different for rep moveS referencing another segment. In reality, you cannot access another segment from the rep moveS. That's why it's saying in the manual, you're copying from DS or ES to DS, right? You don't have the option in that case to override it. So that's actually why this is specified in the manual. Whether you like it or not, this is always moving from this ES to DS. Now, you can change what's in ES and DS, and that's how you can actually change where it's copying from, but the opcode for it will not actually change because there's no notion of variability here. It's saying this opcode is always the literal bytes F3, A5, F that. Yes?
So does that actually mean if the kernel is using FS to indicate where all its DLLs are, that you can change FS on it and have it infinite reference to DLLs? That's...
Well, that's a good question. I can't remember. Let me think. I believe, I'm trying to remember. It's really just a permission issue here. I'm trying to remember whether or not the user space code could change FS. I believe it can, but certainly no legitimate program would change its own. So the point is the kernel wouldn't be fooled. That data structure is exported by the kernel for user space's convenience. So you'd really just be screwing yourself up. So that certainly could be the case. Or maybe you want to, trick the, if you ever get exploited, maybe you want to trick the exploit code, which is going to come in and assume it's all correct, right? Maybe that would work, but I have a feeling other behind-the-scenes libraries would actually die, because if you dig into some libraries as well, you're going to see them accessing the FS0. So that's what I wanted to say about that's one place where there's a convention. Windows is exporting data structure always at FS, and this is one of the points that Christina Johns had brought up in the previous class. She had dug into it, because I had that one question about, I thought I had seen at some point that like the stack cookie on Linux was being stored some offset up from GS. And so I thought, like, is GS on Linux being used as a sort of data structure export thing? And yes, it does appear to be the case that she found something which I need to get into the slides where I was referencing that, yes, Linux, like Windows, is storing some, I think they called it like that thing in the life of binaries, what is it called? Thread local storage. So thread local storage is what they were calling it. So, but it's the same idea. It's just, some thread information which maybe points to some process information and stuff like that. Yep. So basically, each of them has a different segment register, which by convention they export from kernel to user space to store some thread information for that thing. And so when they're switching between different processes, they need to be updating FS or GS so that it points at that process's specific data structure, so that the base address equals, the right place, so that base plus 0 gets you to the linear address, which gets you to the physical address that has the data structure. So, we're actually going to learn a little bit more about that right now by taking some measurements of the FSGS, looking at all the values, literal values in the things, and then comparing them user space versus kernel space. So, and then, yeah, Dave was asking, how about in other instructions, would the opcode change? It turns out the opcode, so if you're hard coding and overriding a thing, like I said, you can do access EAX or you can access FS EAX, right? If you're hard coding it, the opcode doesn't change, but there's something which is at the very end, which we may or may not have time to get to, called prefixes, instruction prefixes. And it turns out if you hard code, this is FS : whatever, there's just like an FS prefix that gets tacked onto the beginning of the thing, so that as the CPU is running through, it says, okay, I've got this prefix, please interpret the next instruction as referring to FS, for instance. So yeah, opcode doesn't change, but a prefix is tacked on to the beginning of the opcode. All right, so for this lab, we're basically going to run something which just takes each of these registers, CS, SS, DS, ES, FS, GS, stores them into data, and then just prints them out. And we're going to do it from user space and kernel space to see what, if anything, differs between them. So to do that, I don't know if everyone has this on your desktop, so I'm going to download it because I don't have it on my desktop. But if you don't have it on your desktop, you need to search for debug view and download that. So debug view lets us see kernel debug outputs without having to actually be in the kernel. So this lets us at least put off for a little while using our VM. So you need to Google for debug view. It should be the first link to the Microsoft thing. Save it to your desktop. And open it up. Drag the exe out to your desktop. You should have a little debug view with a little picture of a magnifying glass covering a bug. I'm just going to walk around quick and check it a little. Right, good. Now, in debug view, once you open it, the key point is you need to so agree to the EULA. And then the key point is right here where it has capture kernel, it's like a little gear with like a red slash through it. You need to click that so that there's no longer a red slash through it, so that you are capturing kernel messages. And then where it says capture Win32, it has the little Windows icon. You want to click on that so there is a red slash through it. So we want kernel messages. We don't want user space Win32 messages. So, and then once you do that, hit this little clear, Control X or whatever to clear out the window. Then, going back into Visual Studio, we want to change our startup program to user space segment registers. So right-click on that, set as startup project. Then we'll just take a glance at the code here. Oh, I'm still running, so stop with the debugging. Set as startup project. Look at user space, segment registers, and you can see really I just have some inline assembly which takes the CS register and moves it to a local variable called mycs, etc. And then I just go through. And now, the only thing here that I did was instead of just printing out the literal value, that's less useful to you. You want to interpret it as a segment selector. So take the bottom 2 bits and say, you know, that's your requested privilege level. Take the next bit and say that's your table indicator, and if it's 0, say that it's GDT, and if it's 1, say that it's LDT, and then take the top 13 bits and say that's your index. So that's what the selector print does, so pretty easy. So set a breakpoint on return hex oddball. I have the best return methods, but I cheated because I just went and looked up, you know, hex words and stuff. Set a breakpoint and run it. All right, and then you'll have to pull up the window again. So what it's saying is, look, the literal value for CS is 1B, hex 1B, but in reality we take those bottom 2 bits and we interpret them. The requested privilege level is 3. We take, you know, the table indicator, which tells us that it's segment GDT, so the table indicator was 0, and then the index, the top 13 bits, is 3. So it looks like everybody here has a requested privilege level of 3. CS is set to different things than SS. DS and ES are set to the same thing, which makes sense for that thing where we were saying, look, you know, if mem move or if rep move or rep stos and stuff like that are using these things explicitly, the OS probably should set them to be the same thing if it wants it to be in the same memory space. FS is set to something different, and GS is set to a literal value of 0, which cannot be interpreted because it turns out that GDT entry 0 is never considered legitimate, and if you have literal 0, you would have index 0, and that's not valid. Well, if you have literal 0 and table indicator 0, which means GDT and GDT index 0, it's not valid. Anyways, GS is not actually being used by Windows in user space. So let's see about kernel space. Now, I hope this is going to work. I didn't test this yet. Well, I think I did. All right, so you need a command prompt. I think I usually test this inside the VM. There should be no difference, but I didn't want to start the VM yet. So this is going to be the annoying part. You're going to, assuming you have, the intermediate x86 on your desktop, you want to change directory to desktop, intermediate x86, intermediate x86 code, and then kernel segment registers. That's desktop, intermediate x86, intermediate x86 code, kernel segment registers. Use tab. And
One direction of slash.
yes. All right, and so once you get there, go ahead and run load.bat. So just run load. All right. And it looks like on mine it failed to start. We'll see though. Actually, I think it always says that. Yes, okay. So it said it failed, but in reality it succeeded because if you go over to debug view, you should see something like this. This is the exact same sort of code with that segment interpretation that was done in user space. So what do we see here? Well, we see segment register, whatever it is. Looks like requested privilege level is 0 for CS and SS, but for DS and ES, it looks like it's still 3 for whatever reason. FS is set to 0, and GS is still not used. So this is looking at our segment registers and just interpreting what they are. So if we want to make some inferences based on that, we want to go back. So I basically took and made that into a table in the slides so that we can do a little. Oh yeah, that's right. I did have pictures in the slides so that if you want to do it on your own. Yeah, these pictures in the slides though are in the context of if you're inside your VM. And, I distributed the VM. And for you, I didn't send the email. So for the people in the class, I'll send you the email where you can get the VM. All right, so when we look at the difference between the two things, what we see is, well, user space looks like they have everything set to RPL of 3. So maybe that's kind of implying that, RPL has something to do with user space in it. Kernel space has a few of them set to 0. Hold on a second. Almost not working.
I think I just got it, but I'm several steps behind.
Okay. Just pop up debug view. You have to have debug view running before. Okay, it is. So then, yeah, you missed this step. Turn off that so I can see it. Run it again. Run it again. There we go. All right, so the difference is RPL is 3 for pretty much everything in user space. RPL is 0 for everything except DS and ES in kernel space. The indices are different, so there's no overlap in user space code versus data segment. So code segment is index 0 or 1 in the kernel, index 2 for data, and then index 3 is code in user space, index 4 is code data in user space. Yeah, GS is always invalid. Looks like FS is different between user space and kernel space. Again, different indices, different RPLs. But the DS and ES don't seem to be changed between user space or kernel space. And yeah, as it says, subject to kernel, different, you look through this on Win 2000 or Win Vista, I don't know if it's going to be the same. But I would expect it would be, except on 64-bit systems, it would definitely be different. All right, so the inferences we get from this is that it looks like CS, SS, and FS are definitely different per user space versus kernel space. And yeah, it's just saying user space versus kernel space. The RPL field seems to correlate very strongly with whether you are in user space or kernel space, right? Except for that DS, ES, which seem to be the same between either. Yep, and that was the other point. It doesn't change DS or ES when moving between, and GS is not used on Windows. So this is just some inferences. I'm not trying to imply anything amazing here yet. We'll talk about. We'll dig down into some of this later, but this is some initial things just by dumping these things You can get a sense of whether it's doing the same thing in kernel space, doing something different, where the privilege levels do or don't matter, that sort of thing. So going back to that picture we had before about how logical addresses are translated to linear addresses, just to reiterate, we know logical addresses are 48-bit addresses that have 16-bit chunk that says, I want to select this segment, and they have a 32-bit chunk that says, I want this offset in that segment. And maybe because some people are wondering, if you have a 32-bit offset, which is greater than the limit of the segment, right? If your segment is, 5 bytes long and you specify an offset of 6, the hardware actually enforces and it says, look, I see that you're accessing outside the segment bounds. It sends a general protection fault, and the processor handles that elsewhere with interrupts, which we'll learn about later. So yeah, the hardware is enforcing whether or not you're overstepping your bounds of these segments, for instance. And the hardware is the one that's actually saying, give me an address, and you give it a logical address, whether it's explicitly logical because you told it the segment, or implicitly logical because it assumes CS for code access and SS for data access. Yes?
So what's enforcing the requested privilege level?
Hardware as well. So he's asking what enforces the requested privilege level, and that's hardware as well. There's a variety, this isn't like the end-all be-all for what specifies ring 0 versus ring 3. So we're not quite there yet. But throughout, as we said, x86 privilege rings are hardware enforced. So the hardware is checking these sort of bits, like RPL, as well as some others we'll learn about in a little bit. It's checking those and it's saying, oh, look, I see you're trying to access, some code segment that is ring 0. And, oh, look, it looks like you're currently ring 0. Hardware says no. Right? So the hardware has built into it these checks on the current privilege level, requested privilege level, etc. Right, so we've got 48-bit logical addresses. Select your segment out of a table. The table can be the GDT or LDT. We said GDT, everybody sees the same thing. LDT, the kernel at its leisure, at its option. What's the word? Say you serve at the what of the king. Is it serve at the pleasure? Is it pleasure? The kernel at its pleasure may, no, it doesn't really work. The kernel may swap out different LDTs for different processes as it sees fit. And whenever you're accessing this logical address, eventually it makes its way to a linear address, which for now we've said is always a physical address. Any questions on what we've covered so far? We haven't seen the segment descriptors yet. We've just seen how you select a segment descriptor with a segment selector. Any questions on anything thus far? Anyone on the phone? So, continuing on. Let's look a little bit.
I do have one
okay.
question. So you have a 16-bit base address there, was it? And a 32-bit offset there. You have 40.
It was not actually. Sorry. Let's see. Well, we're going to dig into it in a second, but from what you've seen thus far, when you're talking about base addresses versus offsets, the base is actually 32 bits. So in these descriptors, yeah, we haven't got to these yet, but it is 16-bit for limit and 32 for the base.
Okay.
And so this is what we're going to go into next. What are those descriptors? What do the structures actually look like? But the two key fields are just, it starts here and it goes to there. All right, so looking at our two different tables, then there's the question of how does the hardware find the GDT and the LDT and stuff like that? Because we said the OS is actually setting up these tables, right? So how does the OS find it? How does the hardware find it? So we saw the relation. Right now we know the relation that the segment selector has the table indicator bit, which is saying, look, this index is either into the GDT or it's into the LDT, right? So TI equals 0, you're selecting from GDT. TI equals 1, you're selecting from LDT. Every entry in these things, which is 8 bytes large, that's why I see 0, 8, 16. Each entry is 8 bytes. Each 8 bytes, and that is your segment descriptor, which we're going to see in a little bit. But for now, we want to focus on how you find it. And so there is a specific register called the GDTR, the descriptor table register, which points at the base of the table and the limit of the table. So it says my GDT starts here in memory, and then it goes to there. And again, it's so you can, well, never mind. And then the LDT turns out to be, well, we'll get there. But what this picture is trying to imply is that the LDT is unlike the GDT. The LDT does not just have a base and a limit that says my LDT starts here and goes to there. In reality, the LDT actually just has a segment selector, and that segment selector selects something from the GDT, and that GDT descriptor has a type of I'm an LDT. And so it actually points at some other chunk of memory. That segment of memory in the GDT is actually an LDT segment. So it's specifying a base and it's specifying a limit, but it's also saying my type is LDT. So if you're trying to access this, if you're trying to access the LDT per process, the kernel would go around and change that segment selector. So let's say it has, 5 LDTs for 5 processes. Process 1, it may have segment selector 10 and for the LDT, and it says if you want to access LDT, the hardware goes to offset 10 in the index 10 in the GDT, and from there it finds the LDT, and from there it goes offset into it. So it's a couple levels of indirection when you're dealing with the LDT, but we'll come back to that in a second. So the GDT for now is the much simpler case, right? There's just a 48-bit register that says the bottom 16 bits in this case. So don't confuse this with logical addresses or anything like that. This is just 16. It's the data structure with 2 fields. The bottom 16 bits is just here's how large this is in terms of bytes. Actually, bytes, yeah, it's bytes. As we said before, the GDT can only have 8,192 entries, and so to the 16 bytes is 8,192. So it's basically saying, here's how large this GDT is, and theoretically it could be less, right? You could specify less than the maximum size, but the point is you can see it goes up to the maximum size of 8,000 entries. And then the upper 48 bits are just the 32-bit base address. And in 64-bit mode, this would be a larger register that would have larger address. So when the hardware needs to access the GDT, it consults the GDT register. And same thing with the OS. When the OS wants to modify the GDT, it checks the GDT register, breaks up those 2 chunks, says, here's the base address, and then, here's the limit. And the OS doesn't really care about the limit that much. It's the hardware, again. Hardware enforces. So if you specify some, you shouldn't be able to, but were it possible to specify, oh yeah, you could. Let's say that this limit for this GDT, okay. Bill, over to the board. Yeah. That, everyone got the password for the VM? No, didn't start the VM yet. Okay. So GDTR says base is right here, and there's some GDT, and then it says...
Hey, Zeno, can you hold on a second? We haven't followed you with the video.
Okay. Bill, can I get the video over the board? Thank you. This right here. All right, so the GDTR has, 16-bit chunk of limit and a 32-bit chunk of base. It says, here's the linear address for my GDT starts, and GDT has a bunch of entries. It says, here's the limit in bytes, which says, this is, say, this could be, only, if you wanted, it could be only 64 bytes large, and then you would only have 8 of these entries in it, right? So if each of them is 8, so this is 8, right? So you could have a small GDT, for instance, right, if you don't want to use all of the memory. And so the point of the limit, therefore, is that when someone's specifying a logical address, we said logical address says, oh, I want index this right here. But what if you have a small GDT, and they say, oh, I want index that right there. I want index 100 in your GDT. But the limit says, no, I'm only really 8 entries large. So this is, again, for the hardware, so that it can, enforce that if someone's coming at it with a logical address that's outside of the bounds here, outside of limit, send a general protection fault, that sort of thing. So I was starting to say, oh, no one cares about the limit. But yes, the hardware does care. And yes, you can specify, if this were not maximum size, which I believe it typically is maximum size, but if it were not maximum size and someone had a logical address which selected outside of it, then yeah, you could have a hardware fault because of that.
If it were not maximum size, where would a program get the information about what ranges of addresses are valid?
Well, it would certainly have to be minimum size, and minimum size would be at least, you know, 2 things for a code and segment. Let's say simplest possible case, everyone uses the same code and data segment, so it could only have that, right? And they could, you know, completely cover all of memory, so that's all you would really need. So in the more complicated case where you have FS pointing at different data structures all over the place, then, you know, depending on how your OS wants to use it, the minimum size is something different. So you don't need maximum size in order for everything to know where to find stuff. It's just a question of what does your OS actually want to do with it.
Does the OS usually publish that size in a place that programs do
Not
get at it?
really, because this type of stuff is typically the kind of thing that only the OS deals with, and they don't want other third-party software messing with it. Third-party software could mess with it, but it's not something where they have any, you know, API documents saying, oh, if you want to, you know, register a new GDT entry, do this and that. It's kind of, they do what they're going to do for their purposes. It's really not something anyone else is meant to mess with. But messing with it does cause problems, as we found when we found a new attack, which I'll maybe talk about later. All right. So this is pretty much it. There's 2 new instructions here. The stars, LGDT for load 6 bytes of memory into the GDTR, right? So 2 bytes for the 16-bit part, 4 bytes for the 32-bit part. Take something out of memory, load that into the register. Store GDT says take that register, dump it off to 6 bytes of memory. So if you want to look at the base and the limit of the thing, you use the store, you store it out, and you start doing it. Turns out the load is ring 0 only, so only the kernel can be changing around different base address for the GDT and stuff like that. You don't want user space code pulling the GDT out from underneath you. Store, though, however, is unprivileged, and anyone can do that. And so we'll get to a point later about when we deal with a lot of these registers we're going to talk about for segmentation and interrupts and stuff like that, there's a funny abnormality in Intel specification in that the only people who would ever have any cause to change these things is the kernel. For some reason, they had the reading the register out was available to user space, and that's the basis for a couple different virtualization detection things. So they read out the register and, oh, hey, look, it doesn't look like a normal Windows register because the virtualization system ended up changing it. All right, so that's all I want to say about GDTR for right now. The point is, it's just how the OS or the hardware finds the GDT, because we know that hardware needs to find it when you're specifying a logical address. The hardware needs to break down the logical address, take table indicator, take index, walk to this table, find each of those descriptors, read whatever data is in the descriptor, we don't know yet, but, you know, figure out whether you're trying to access outside the bounds of some other, you know, segment descriptor, etc. So then, with the LDT, we said if someone were to make use of the LDT, and the point is, after this class, you can go write your own OS and you can say, by gum, I want to use the LDT. The LDT register is in reality only a 16-bit segment selector. And all it does is it selects a segment which must always be selected from the GDT because you can't find the LDT by selecting something from the LDT. The point is, how you find the LDT is you take this segment selector, break it down. It always must have a table indicator of GDT. And then you say whatever this index is, that's an index into the GDT. And that specific descriptor in the GDT should have itself marked as, hey, I'm an LDT. And it should say the LDT has a base address of this and a limit of this, because those are information that are in those segment descriptors. So, like this kind of says right here, in the segment descriptor, which is going to get loaded and it's going to get cached in an invisible area again, when the hardware is trying to access the LDT, it walks one time to the GDT, finds the entry, pulls out the base and the limit for the LDT and caches that so that forevermore, when you try to access something with a logical address that points into the LDT, it just knows, here's the base. How many steps do I need to make into that table to find the next descriptor? All right, and again, 2 instructions. LLDT, take and go ahead and load up that new segment's So the point here is if the OS wants to have a different LDT for different processes, each time before it swaps into the context of a new process, it would say, okay, I'm going to load my LDT to now be index 11, to now be index 12, to now be index 13 in the GDT, so that each of those indices points at a different base and address and stuff like that, so that they're not overlapping between processes, etc. And again, store, so LLDT, that's privileged, only ring 0 can set LDT values. Reading it out is unprivileged, and user space code can do that. And like I was saying, this is the basis for one anti-virtualization detection mechanism, which I'll cite here at the end of this deck. All right, so now what are the segment descriptors actually? Right, so we've been referring, we got tables of segment descriptors, but what's actually contained therein? We know they got a base and we know they got a limit because they're specifying some memory range, which is a segment. But what else? All right, so how they're actually broken up, this is, you know, a 64-bit data structure. And so the first 16 bits here are the first 16 bits of the segment limit. But it turns out the segment limit is not actually, so, actually, I think I've been misdescribing this throughout. Yeah, see, that's the table limit, that's 16 bits. When we were back up here, where we first saw this, heuristic sort of view of things, I said this is 32-bit base, 16-bit limit. In reality, this is a 20-bit limit, and you'll see why in a second, but a 20-bit limit is required in order to access all of memory if you're accessing memory in chunks of 4K. So 2 to the 20 times 2 to the 12, because 4 kilobytes is 2 to the 12. It's like FFF. 2 to the 20 times 2 to the 12, add the exponents, 20 plus 12, 2 to the 32. So you can access all 32 bits of memory if you have a 20-bit thing, and you're saying, hey, I want to access, my limit is not actually in bytes, my limit is in 4 kilobyte chunks. That was my bad on describing that wrong before. But when we get into the actual details, we can see that it specifies first 16 bits of the limit is here. Second 4 bits of the limit is right here. And so then there's this other field, granularity, G, right there. Granularity says, is this limit in bytes or is this limit in 4 kilobyte chunks? So in that way, you could specify like, hey, I only want, something to be 4 kilobytes big. Well, no, 2 to the 20 in bytes is like whatever it is. It's 4 times 4, 16. It's like a megabyte. See, I thought it was a megabyte, but I'm really bad at mental math. So, because yeah, I seem to remember something about like DOS could only access a megabyte worth of memory at a time or something because of this 20 bits, because it couldn't use these 4 kilobyte things. So, anyways, 20-bit limit, which says, how big of a chunk of memory this segment is. And then we got base address is all chopped up all over the place, but 16 bits of it here, 8 bits of it there, 8 bits of it there. But, the hardware puts it all together and says, here's my 32-bit base address. This is the linear address, which is the base of a segment. And then we got a bunch of different, fields. So, all right, so we saw the base, 32 bits. We saw the limit, that's 20 bits, which is required to access all of 32-bit memory. Granularity, as I said, if it's 0, it says treat this limit as the number of bytes. If it's 1, it says treat the limit as the number of 4 kilobyte chunks. All right, DB, default operation size. This is an interesting thing I'll talk about in the next slide, but in the intro class, I'd given you a lying simplification in terms of, I said, I'll talk about it in the next slide. But this is what controls whether or not instructions are treated as 16-bit instructions or 32-bit instructions, as well as whether memory access is treated as 16 by default or 32 by default. All right, and then descriptor privilege level. Here's a nice another 2-bit field having the name privilege level in it. And so descriptor privilege level is, to cut to the chase, it is saying whether or not this descriptor describes a chunk of memory which is going to be ring 0 or ring 3. So ring 1, 0 through 3. So we already saw requested privilege level is in a segment selector. We now have a descriptor privilege level. So we're almost to the point where we can really just understand whether stuff is executing ring 0 or ring 3. Not quite there yet. But we're most of the way here, because we can see a segment specifies this chunk of memory, and it can specify, oh yeah, that's a ring 0 chunk of memory. So if it's a code segment, maybe that's a ring 0 chunk of code. All right, but so the one thing I wanted to clarify from the lie that I told in the intro class is we had seen sort of at the very end quickly, when you go into the manual and you look at the actual opcodes, there can be ambiguity here in that it says an add instruction is either, for the same opcode, you're either, the processor is reading in byte 05 and it knows, aha, an add immediate is coming up. But then the question is, in this syntax, it's saying immediate word, which is words are 2 bytes in Intel's world. So immediate word, so it's say, if the processor sees 05, it should expect 2 bytes after that, and it should add those 2 bytes to AX register, right? But we have the exact same opcode byte, 05, and now in this other form, you get 05, and you instead expect to take 4 bytes and add it to EAX register, right? So how does the CPU actually know what's going to go on here? When it sees this ambiguity, how does it know what to do? And the answer is based on the DB field of the segment, whichever it's executing it. So if you've got a code segment, and this DB field back here is set to 0, the processor knows when it's reading in code from that segment, it should treat those opcodes as 16-bit instructions and 16-bit words and everything else. And if it sees that that chunk of memory is set as DB1, it should now interpret everything as 32-bit. So this is the way that it actually decides whether it's executing 32 or 16-bit code. Obviously, if you're in something like real mode, we said is like a hard-coded lockdown. This is 16-bit mode. Well, actually, I shouldn't say that. I haven't had enough experience with real mode that I can really say you can't access 32. I have a feeling like you probably can. And so later on, if we make it to the end, there's again a different type of instruction prefix which you can use to override this. So if you're in 32-bit mode and you want to access a 16-bit instruction, you tack a little thing onto the front of the instruction opcode sequence. So instead of 05, it would be some prefix 05, and then the CPU would say, aha, I need to read 2 bytes rather than 4 bytes. So you can override this, but by default, whatever your segment says, that's whether you're executing in 32-bit or 16-bit for code and data access. But most protected mode OSs, of course, they're going to be executing in 32. That's why we always just assume 32-bit. All right, a couple last thing. There's an L flag which says, is this a 64-bit segment? We don't care about that for this class. There's an S flag saying whether this is a system segment or a code or data segment. So there's 2 classes of segments. There's system, which has a bunch of different special descriptors, such as the LDT. And then there's coded data. And for the code and data, there's a bunch of variety of them of whether they're currently set to read only or read write or different options like that. So there's 4 bits specifying a type. And so in reality, you kind of have 5 bits of different things. So system can be 0 or 1. And for system equals 0, you then have 4 bits specifying all the different types of system ones. And for system equal to 1, you have 4 bits specifying all the different types of code or data segments. And we'll see the table of that in just a second here. Finally, there's the present flag, which is just saying, like, if for whatever reason the operating system wants to swap in and out segments and say, like, sorry, this one's not available now, but we'll get it back later, the OS can set present to 0 on a flag. And so then if someone specifies a logical address which selects that segment, the hardware will automatically check this present flag and say, aha, you tried to specify a segment which isn't really here right now, throw up a hardware fault, catch an interrupt, etc. Whatever, not present exception. All right, so this is sort of the breakdown. We don't really care about all of this, but this is just to kind of give you a notion. So when the system bit is set to 1, saying like this is a code and segment and not system, which I know is counterintuitive. When system is set to 1, it's code or data, and then you consult the type to understand what type of code or what type of data it is. So for all of the most significant bits equal to 0, it's always data. All for the most significant bits equal to 1, it's always code. And then from within that, there's code read-only and code read-only access. It's saying like someone's actually touched this memory, but we don't care about that most of the time. There's read-only, there's read-write, but then there's interesting things. There's read-only expand down, and there's read-write expand down. Expand down segments, rather than being base plus limit to tell you what's in bounds for this segment, so that the hardware will check base plus limit, and if you're not within that range, then you get a fault. Expand down segments, it's base minus limit, and then if you're not within that range, you're out of bounds. And so someplace you might use that is, for instance, the stack. We said stacks grow towards low addresses. So maybe you want to set the base address at the top of the stack, make the stack highest memory address, and then you say, I have an expand down segment, and then that sort of makes sense with stacks. They don't actually do it that way. Just say. But there was like an exploit. I don't know the exact nature of it, but I'll give a link to it later. There was a case where someone had done, see, the point is, it's hard to say something is an exploit when you're already in the kernel and you can already change stuff, but there was an error condition that they could mess with the operating system by setting expand down segments. I think it would actually call it an exploit in the sense of access control bypass more. So it's more like there was an expand down segment, and whereas the operating system would normally, not give you access to this memory, the expand down segment was such that it was within bounds. So that was one case where someone knowing this detailed type of thing was able to say, aha, what if I do that? How will the operating system respond? And it obviously responded in error because it's not expecting to ever see that. All right, anyways, then for our code, we have execute only and execute read. So first of all, we can see right now segments already have the ability to hardware enforce. Look, if you've got a data segment, your CS segment selector should never point at a segment which is described as a read-only or read-write thing. That's not executable. Your CS must always point at some segment which has its type of code, and then it can be execute only or execute read, but not execute write. Right? So you may not write to your code. And then there's these other notions of conforming. So this is called non-conforming, and then there's conforming. With regular non-conforming, although again it's counterintuitive, non-conforming is the norm. For non-conforming things, you may not read from, you may not jump in your code from ring 0 to ring 3. Let me think, is that right? You may not jump from ring 3 to ring 0. Okay, so for normal stuff, you may not jump from ring 3 to ring 0, which makes sense. The user space code should not be able to jump into the kernel and start executing stuff, right? Conforming is the backwards of that. You may not jump from 0 to 3, but you can jump from 3 to 0. But it's still sort of secure, and it still all works out, because even though your ring 3 code can jump into this ring 0 segment and execute, the ring 3 code has not had its technical privilege level changed to ring 0. It's still ring 3 code. It just happens to executing in the code segment of the kernel. But it can't execute instructions which can only be done by ring 0, for instance. So if it jumps into that code and says, hey, I want to load up the GDT, it's not going to work. Anyways, there was in Greg Hoglin's FRAC article on rootkits, like 1999, he had said, hey, we can set these code segments backwards, and that can be backdoor, and that user space code can execute kernel code. And yes, that's true, but one, it can't access privileged instructions, and two, in reality, in modern operating systems, the privileged stuff is actually enforced more on the paging, which we learn about later. So it turns out the paging permissions are such that your ring 3's code can't actually access any of the ring 0 code. So I don't know if that maybe made sense at some point in NT or Windows 2000, but I don't care to go back and check. All we know is it definitely doesn't work on XP or anything new.
Hey, Zeno?
Yes.
Is expand down used in relation to local variables?
No, not really. So we did say before, right, we have the notion of stack, and we have the notion that stacks expand down, and stacks have our local variables and stuff like that. But when we get to the surprise ending here, we'll see that no, the using a data segment which expands down is not actually going to have any relation to local variables. So yes, I'll keep just what's the word, leading on. I don't know, for some other freaking sounds bad. I don't know what the correct phrase is. just going to keep leading you along until we finally get to the surprise ending. So I'm not answering questions, but I'll hopefully come back. The problem is I'll probably forget them after lunch. And actually, I need to go set up LunchCon. So here's the system segment stuff. The only thing we've actually seen that makes any sense to us thus far is this one right here. There you go. A segment descriptor may say, hey, I am of type LDT. And if so, then the GDT can index into the LDT register will point at that segment. And then if you have a logical address which has a segment selector which has table indicator of 1, it'll say, aha, I know that I need to access the LDT, and the hardware will, on the first access, cache the information about the base of the LDT as a limit. So that's it for now. Anyone have any questions thus far? We're going to get back to the lab here in a second and dig into this and look at the things in WinDebug. But does anyone have any questions about what we've now learned about segment selectors, segment descriptors? Segment selectors select these data structures and they describe chunks of memory. Anyone have any questions thus far?